Okay, so today we are going to discuss chapters 23, 24, 25, and 29, the four chapters that will be on exam number 3. Just briefly, in general, in regards to exam number 3, there shouldn't be any surprises. You will have seen all the types of problems that will appear on you've seen those types of problems on previous exams. But I will reiterate something I said in class today, which is that chapter 29 will be covered a little more superficially than the other chapters. You won't see any of the reactions from chapter 29 in a synthesis problem because we haven't learned very much about how to link those reactions up with other reactions. And then also, you won't see challenge level problems related to chapter 29 just because we're covering transition metal chemistry at a fairly superficial level. However, you can expect to see mechanisms from chapter 29, and you will need to be able to draw those mechanisms. As we mentioned in class today, you don't use curved arrows for the palladium mechanisms. But there are some that we'll learn on Monday that you will be drawing curved arrows for. And then, of course, you'll need to be able to predict the products of reactions from chapter 29, as well as provide reagents or catalysts. So less emphasis on 29 than the other chapters because we're spending less time on it and we're covering it superficially. But please don't ignore chapter 29. Every year there's a few students who ignore this chapter and they're very disappointed when they take the exam as a result. So with that, let's go into a discussion of chapter 23. So chapter 23 was entitled Substitution Reactions of carbonyl compounds at the alpha carbon. So this is where we first talked about using carbonyl compounds as nucleophiles. And we started off this chapter discussing enols. We'd learned about enols previously as the tautomers of ketones and aldehydes. We know that enols are less stable in most cases than aldehydes or ketones, but we did talk about enols from 1,3-dicarbonyl compounds and why they're more stable than the carbonyl compounds themselves. And we talked about the tautomerization mechanism. So an enol is a tautomer of an aldehyde or a ketone. So the process of converting an aldehyde or a ketone into an enol is known as tautomerization. And we have mechanisms for drawing a tautomerization in acid or base. So you should be able to draw that mechanism in either acid or base. Then we learned about enolates. Enolates are negatively charged. They are the conjugate bases of our aldehydes or ketones. They're also the conjugate bases of enols themselves, but they're usually generated by deprotonating the aldehyde or the ketone. So we learned about relative basicity of different enolates. Enolates are basic and nucleophilic, and we determined or ranked their relative basicity by considering the pKa's of their conjugate acids. So there was a table in the book, table 29 must be 23.2, sorry, I can't read my own notes. Table 23.2 was a table that showed those pKa values of aldehydes, ketones, esters, nitriles, 1,3-dicarbonyl compounds. And so that table is a good place to review that information and not to memorize the numbers in the tables, but to make sure you understand the orders, to understand why a ketone is more acidic than an ester, why an aldehyde is more acidic than a ketone, and so forth. So if you can look in that table and you can understand the relative positions of those carbonyl compounds in the table, then you'll be in good shape. The only one you really have to memorize is the nitrile. There's really no good explanation as to why the nitrile falls where it does in the table. So there you just have to memorize that a nitrile is essentially as acidic as an ester. It has basically the same pKa. But other than nitriles, the positions of the other compounds in that table you should be able to understand based on basic principles such as whether a group is an electron donating group or not. Okay, so enolates are formed by deprotonation of a carbonyl compound. So we talked about the bases that are used to form enolates. And there were really two categories of those bases. We can use hydroxide or alkoxide bases such as ethoxide or tert-butoxide. And the key thing with those bases is that you're going to get a small or low concentration of your enolates. And most of your aldehyde or ketone will remain as an aldehyde or ketone. As we learned in chapter 24, that's useful in some cases. But of course, these bases will quantitatively generate enolates from 1,3-dicarbonyl compounds. Okay? Our 1,3-dicarbonyl compounds are more acidic, and they will be deprotonated quantitatively to give you 100% of the enolate from those types of compounds. And then we had LDA. All right, so the features of LDA, it is a strong, I should say very strong, these are strong bases, hydroxide and alkoxides. LDA is a very strong, bulky base. Because it is bulky, it functions only as a base and not as a nucleophile. And so LDA is able to quantitatively generate enolates. You get 100% of the enolate and you won't have any of the carbonyl compound remaining. So also in regards to enolates, we learned about two types of enolates. Our kinetic enolate. So the enolate that is formed the fastest, that is our less substituted enolate. And we said that if you're going to generate a kinetic enolate, you want to use LDA, you want to use an aprotic solvent, you want to use low temperatures. We explained why that was the case, so you should understand why these are the reaction conditions for generating kinetic enolates. And then we have the thermodynamic enolate. The more substituted enolate, which is formed more slowly, so we have to rely on equilibration. We have a different set of conditions there. We want to use our alkoxide bases, our bases that only generate a small amount of enolate and leave a large amount of that carbonyl compound remaining. We want a protic solvent, and we run the reaction at room temperature as opposed to a lower temperature. So understanding the reasoning for these reaction conditions is important. And then we talked about a process that can happen when you generate an enolate from a carbonyl compound. That is racemization of the alpha carbon. If the alpha carbon is a stereocenter and you make an enolate, you've now destroyed that stereocenter. If you reprotonate it to go back to the aldehyde or ketone, you'll end up with a racemic mixture. So that's something to be aware of. We then started talking about reactions of these enols and enolates. And the first one we discussed was the alpha halogenation. We've had many different types of halogenation reactions during both 351 and 352. This one installs a halogen alpha to a carbonyl group. And this one is unique from our other halogenations because we can use chlorine, bromine, or iodine. We're still not using fluorine, but we've added iodine now to the list that work in this reaction. And there were two versions of this reaction. We had the acid catalyzed version. Okay. That typically involved the use of acetic acid as the solvent and also as the acid catalyst. So you should be able to draw a mechanism for that reaction. And then we had the base promoted halogenation. And we say base promoted because the base was consumed in this case. It's not regenerated. And so the problem with the base promoted reaction is that polyhalogenation can occur. The acid reaction is best for the acid promoted reaction is the one you would use for installing a single halogen on an alpha carbon. And then the base promoted reaction gives polyhalogenation, so you would want to use that if you wanted to replace all of the alpha hydrogens with a halogen. And then a special version of this was the haloform reaction. The haloform reaction was where we would take a methyl ketone, convert all three of those alpha hydrogens into halogens, and then we could have a leaving group, a trihalo carbon leaving group, and end up with a carboxylic acid. So that's a reaction that you should understand the mechanism and be able to predict the products of. Okay. So then we talked about the reactions. We briefly talked about reactions of alpha halo carbonyls. And there's really nothing special about this, to be honest. We've learned previously that our alkyl halides can undergo substitutions and eliminations, and that's exactly what happens with these compounds. So it allows us to replace a hydrogen with a halogen, and then usually that halogen undergoes either an SN2 reaction or undergoes an elimination to make an alkene. Okay, then we moved on and discussed enolate alkylation reactions. This is where we're using our enolate as a nucleophile, and we're using alkyl halides as electrophiles. So this is important because we're forming a carbon-carbon bond. But there were some restrictions here because the enolate is much more basic than the nucleophiles we saw with SN2 reactions last semester. We're restricted to methyl halides and primary alkyl halides in this reaction. Okay, the secondary alkyl halides would undergo elimination due to the high basicity of those enolates. And then we learned about two processes that allow us to avoid some of the limitations of enolate alkylation reactions. We discussed some of those limitations in class, and then we talked about these two methods. One is the malonic ester synthesis. And in the malonic ester synthesis, we end up with alpha alkylated acetic acid derivatives. Okay. So when it's all said and done, you have the elements of acetic acid, and then you have either one or two alkyl groups attached to that alpha carbon, depending on whether you performed one alkylation or two alkylations. Okay. And then we had the acetoacetic ester synthesis. So the malonic ester synthesis uses a 1,3-diester as the starting material. Acetoacetic ester synthesis is using a beta-ketoester, ethyl acetoacetate, as the starting material. And this gives you alpha alkylated acetone. And we explained in class why you would use acetoacetic ester instead of making an enolate from acetone itself and doing the alkylation. But this can attach one or two alkyl groups at the alpha carbon of these compounds. And as I mentioned, it is quite useful in multi-step synthesis problems. It does enable you to form carbon-carbon bonds and make larger molecules from smaller building blocks. So you might see it in that regard. So you'll need to be able to use these methods in a multi-step synthesis. You'll need to be able to look at a target compound and decide which of these two methods is the right one to use. Okay? And I've given you the clues right here. If you're making a ketone, you'd be using acetoacetic ester. If you're making a carboxylic acid or one of its derivatives, then you would want to use the malonic ester synthesis. And remember, one of the components of these syntheses is the decarboxylation reaction. So in conjunction with learning the malonic ester synthesis and the acetoacetic ester synthesis, we also learned about decarboxylation. We learned that if you have a carboxylic acid and you have any kind of carbonyl, it could be another carboxylic acid or it could be a ketone, in a 1,3 relationship, then that carboxylic acid undergoes decarboxylation. So you should know the mechanism for that decarboxylation process. All right, so that sums up the topics from chapter 23. Let's take a look at chapter 24 now. We'll start that over here. So chapter 24 was entitled Carbonyl Condensation Reactions. So these were more reactions of enols and enolates as nucleophiles, but they involved reaction with carbonyl compounds, other carbonyl compounds as the electrophiles. And we started out with the aldol reaction. Where we're reacting an enolate from an aldehyde or a ketone with the parent aldehyde or ketone. The simplest version of the aldol reaction is the self-aldol, where it is two of the same molecule reacting together, an enolate reacting with the aldehyde or ketone it was derived from. We said that that process is thermodynamically favorable for aldehydes, but not thermodynamically favorable for ketones. A couple of other things we mentioned about it was that for the self-aldol, you need a low concentration of the enolate because you need most of it to remain as the aldehyde so that it can, the enolate can attack the aldehyde. We learned about the elimination process, or maybe I should say dehydration. So we can eliminate out hydroxide, which is a dehydration. If the dehydration is not performed, then the self-aldol is a reversible process. And so it only proceeds forward with aldehydes and not with ketones. But if you perform the dehydration, that is irreversible. So then you could drive forward an unfavorable process, including one involving ketones. A few things about this elimination or dehydration. It has its own unique mechanism. We referred to it as the E1CB mechanism. And the CB, usually the C is written lowercase and the B is capitalized. Doesn't really matter, but refers to E1 conjugate base, meaning that we deprotonate the hydrogen first, giving the conjugate base of our beta hydroxycarbonyl compound. Then we eliminate out the OH group. So please remember that. Students tend to want to draw the mechanism of this dehydration as an E2. It is not an E2. If you draw it as an E2, you won't get credit for that. So please make sure you learn and are able to draw the E1CB mechanism. And then we also learned that this elimination or dehydration is spontaneous if that double bond is conjugated not only with the carbonyl, but also with something else, such as a benzene ring or a second carbonyl group. But otherwise, in simple self-aldols where there's no additional conjugation, then you have to heat up the reaction mixture in order for that elimination to occur. And if you remember that simple rule, it can help eliminate some confusion related to whether or not the dehydration will occur. Okay? So, and then we also learned, because the aldol reaction is reversible, if you don't have the dehydration step, without the dehydration being reversible, you can also have retroaldol reactions, where you can take a beta hydroxy carbonyl compound, treat it with base, and actually cleave a carbon-carbon bond, and that will give you back an aldehyde and or a ketone. And we had a little more to say about that in the section on the biological reactions, because that does happen in nature. Okay, so in contrast to the self-aldol, we had a version of the aldol called the crossed aldol. Generally speaking, if we try to use two different aldehydes or ketones in an aldol reaction, we could get 4 possible products. So generally, a crossed aldol reaction is not useful. We had 2 versions that are useful that we mentioned in class. We said that if only one of the aldehydes or ketones has alpha hydrogens, and then we use the one that doesn't have alpha hydrogens in excess, then that will give us a single product. And then we also said a crossed aldol reaction between a 1,3-dicarbonyl compound and then an aldehyde or a ketone, that kind of crossed aldol would be favorable. So 2 instances where crossed aldol reactions are useful. Another version of the crossed aldol was called the directed aldol reaction. That was where we would take the aldehyde or ketone that we want to make the enolate from, and we would use LDA to make 100% of the enolate, and that would give us, of course, the kinetic enolate. And then after we generated the kinetic enolate, we would then add in the second aldehyde or ketone, the one we want to use as the electrophile. And so because we make the enolate first from one of the aldehydes or ketones and then add the second one separately, that's how we direct the aldol to occur in the fashion that we want. Okay? And then our last aldol reaction that we talked about was the intramolecular aldol reaction. And that reaction was used to generate 5 to 6 membered rings because those are our most stable rings, the ones that are free of ring strain. And so we showed you how even if you could generate multiple enolates from your starting material, usually only one enolate would be able to cyclize to give a 5 to 6 membered ring. So only one enolate would be able to go forward. And then these intramolecular aldol reactions were made reversible, typically by heating them up to perform that dehydration. Okay? All right, so we've filled up the board. We'll take a quick break and do some erasing and then continue on with chapter 24. You can go ahead and erase that too. All right, so after we learned about the aldol reaction, we then learned about the Claisen reaction. So the Claisen reaction, like the aldol reaction, is a condensation reaction between two carbonyl compounds. But because it uses esters instead of aldehydes or ketones, the products of a Claisen reaction are beta ketoesters. The mechanism is important. It's a nucleophilic substitution as opposed to the aldol being a nucleophilic addition. And then the key thing about the Claisen mechanism is that it is irreversible. The aldol reaction is reversible if you don't perform the dehydration. The Claisen reaction is irreversible because there's an acid-base step. You have a leaving group that is a strong base, and when that leaving group departs, it will deprotonate the beta ketoester that is generated, so we have a second step where we add acid to the Claisen, to the reaction in order to generate the beta ketoester product. So understanding and being able to draw that mechanism is important. Okay? So the simple Claisen reaction is a self-Claisen similar to the self-aldol involving two of the same esters. But then we can have a crossed Claisen reaction. And similar to the crossed aldol, crossed Claisen is only useful in certain circumstances. If we have a case with only one of the esters having alpha hydrogens, and then we use the one without alpha hydrogens in excess, we can accomplish a crossed Claisen. And then we also learned that because ketones are more acidic than esters, and the self-aldol of ketones is unfavorable, we can make the enolate from a ketone and react it with an ester. And in that case, we get a 1,3-diketone as the product instead of a beta ketoester. On the topic of crossed Claisen, we also learned about two other electrophiles that can be used in Claisen reactions that are not esters. These electrophiles are one oxidation state higher than esters. They're at the CO2 oxidation state. We had a chloroformate and a carbonate. And when we use these other electrophiles, we can actually generate 1,3-diesters. You can synthesize malonic ester using this method. So we have a couple different variants of the cross Claisen with some different electrophiles that you need to be aware of. And then our last version of the Claisen that we talked about was the Dieckmann reaction. And the Dieckmann reaction is simply an intramolecular Claisen reaction. Like the intramolecular aldol, it is used to form 5- and 6-membered rings. So if you have a diester, you can generate a cyclic, a 5- or a 6-membered beta ketoester via a Dieckmann cyclization. Okay, then we spent a little bit of time talking about biological aldol and Claisen reactions, reactions that occur in nature, in living systems. Okay. And there were really three types of those reactions that we talked about. The aldol, and what we said about the biological aldol reactions is that enols rather than enolates are used as the nucleophiles. You typically don't have strong bases capable of generating enols in high concentration in living organisms. So using enols as the nucleophiles works better. And we noted that in many times in an aldol reaction, stereocenters are formed, and the enzyme can control, since the aldol reaction is catalyzed and performed in the active site of an enzyme, the enzyme can control the formation of the desired stereoisomer. We also noted that the proton transfer steps can be combined with other steps. We wouldn't do that for a reaction occurring in a flask, but in the active site of an enzyme, you can have three reactants held together in close proximity, whereas that doesn't happen without enzymes. We also talked about the Claisen, biological Claisen reaction, and a couple things about that. In nature, it usually involves thioesters. Nature uses thioesters more than esters in these types of reactions. And then the other thing we noted here with biological Claisen reactions is they do involve enolates, but the enolates are formed via decarboxylation, okay? So you would have a thioester, and then you would have a carboxylate attached to the alpha carbon, and the enzyme promotes that decarboxylation. There's not enough heat present in the living systems to have that spontaneously happen as it would in a flask if you applied heat, but the active site of the enzyme is able to catalyze that decarboxylation. So that's a way that living systems are able to form strongly basic nucleophiles like enolates without using strong bases, okay? And then the final thing we had in this section was the retroaldol. We'd already mentioned earlier in the chapter that retroaldols can occur, and then we showed you that retroaldol reactions are common in nature as part of metabolism. Metabolism is usually the reverse of synthesis. We're taking larger molecules, breaking them up into smaller molecules, and then by virtue of some of the reactions going on there, we're able to release energy when that happens. Okay, so retroaldol as part of the metabolism, part of the glycolysis process. Okay. All right, so then we moved on to a couple of other reactions to finish off the chapter. We had the Michael reaction. So the Michael reaction is an example of a conjugate addition or a 1,4 addition, where we're using an enolate as a nucleophile, adding to the beta carbon of a 1,4 dicarbonyl compound. It doesn't always use a 1,3 dicarbonyl compound as the nucleophile, but most cases, most of the examples we have in the book, most of the examples you'd see in a Michael reaction involve the enolate of a 1,3 dicarbonyl compound adding to the beta carbon of another carbonyl compound. And then we finished with the Robinson annulation. And the Robinson annulation had nothing new in terms of the reactions and the steps involved, but it just combines a lot of processes. Annulation means ring-forming reaction. So we form a six-membered ring, specifically a cyclohexenone, six-membered ring with a carbonyl and a double bond. So it's important to both be able to draw the products of a Robinson annulation and to be able to use a Robinson annulation retrosynthetically to take the product, the cyclohexenone product, and figure out which two compounds would be combined in a Robinson annulation to make it. So the Robinson annulation involved three processes. It starts with a Michael reaction. Then after the Michael reaction, it has an intramolecular aldol reaction. And then it concludes with the dehydration. That's what makes it irreversible. And because we have the dehydration, we have to use heat when we're performing a Robinson annulation. So that's what would allow us to stop at the Michael reaction if we were wanting to perform just a Michael reaction and not the whole Robinson, is to do it at room temperature. Okay? All right, so that finishes chapter 24. Now let's look at chapter 25, which was on amines. Okay. So amines are special, as we learned. They are the most basic of our neutral organic compounds, because nitrogen is our least electronegative atom that has a lone pair. The first thing we learned in this chapter was some vocabulary. How we classify our amines, primary, secondary, and tertiary. We learned some basic nomenclature. As always, you don't have to know how to name complicated amines. If you can name the simple ones that we used as examples in class, you'll be fine. And nomenclature on this exam will primarily be tested indirectly, where you'll see names in the problems and in the answers as opposed to structures, and you'll have to know what structures those names represent. We did have a few common names. Pyridine and pyrrole, and then the saturated versions of those, piperidine and pyrrolidine. So those common names we learned in class, you do need to know what those names represent. We talked about the physical properties of amines. And there were two key features there. One was that tertiary amines cannot hydrogen bond to each other. They can hydrogen bond to water molecules, of course, so they can dissolve in water, but they're not going to be able to hydrogen bond to each other, so they have lower boiling points than other types of amines. And then we also learned that the hydrogen bonds involving NHs are weaker than hydrogen bonds involving OH bonds. And we talked about why that was. Of course, we had a quiz on that too. So hopefully you're familiar with that particular topic. We spent a little time reviewing spectroscopy of amines. In the mass spectra, we have our nitrogen rule, and so that's something that's important to remember about amines. In the IR, we had the NH stretch, which appears in the same region as the OH stretch does, but we learned that it is there's two peaks if you have a primary amine, one peak if you have a secondary amine, and of course no peaks if it's a tertiary amine because there's no NH. And then we briefly talked about the NMR, where the hydrogens alpha to a nitrogen are going to be de-shielded, but less de-shielded than hydrogens alpha to oxygen. So they're in about the 2.3 to 3 range. We also mentioned that NH peaks will not have splitting for the same reasons that OH peaks don't have splitting. Okay. Then we spent some time talking about how to prepare amines or synthesize amines. And we started by reviewing some chemistry that we had learned previously. and also some new versions of chemistry that we'd learned previously. So we talked about SN2 reactions. We said that we could use excess ammonia, and that would enable us to synthesize primary amines. We also said that we can use SN2 reactions to make quaternary ammonium salts. That's part of what is done in the Hofmann elimination, for example. That's where we saw an example of using excess of iodomethane in that case to generate a quaternary ammonium salt. But when you want to control the reaction and you want to make a primary amine from just one alkyl halide, one equivalent of an alkyl halide, then you can use the Gabriel synthesis. Okay, so the Gabriel synthesis was a way to avoid the polyalkylation problems that happen when you're using amines as nucleophiles, right? Amines as nucleophiles are prone to polyalkylation, and you can only suppress that by using excess ammonia. So in other cases, you can use the Gabriel synthesis. That allows you to avoid polyalkylation. We're using the conjugate base of phthalimide. So we drew the structure of phthalimide for you. It has a pKa of 10. We can deprotonate it with hydroxide, and we can make a nucleophile, a nitrogen-centered nucleophile that will react with primary alkyl halides. And then, of course, we have to cleave off the phthalimide group to get the primary amine. Then we learned about reduction of nitrogen-containing functional groups as a way of synthesizing amines. And there were several of these that we had. Most of these we'd learned how to reduce before, reducing a nitro group. One we learned about that we hadn't learned about reducing before was reducing the azide. Remember, that one was not in the book, but I told you that that's a very useful way of generating amines. You can also reduce nitriles to get amines. And we said that if you perform an SN2 reaction with cyanide and then reduce that to get an amine, you convert your alkyl halide into a primary amine by adding a carbon. And so that's a little different than using azide or the Gabriel synthesis. You're not adding carbons in those other cases. And then we talked about reducing amides. Okay, that also allows us to generate amines. And reducing amides is versatile because that allows us to form primary, secondary, or tertiary amines. Then we had another reduction-based method of forming amines, and that was reductive amination. Reductive amination uses a new reducing agent, new to us at least in the class, and that's sodium cyanoborohydride. And we talked about how this is a weaker reducing agent than sodium borohydride. So it will only reduce iminium ions, and it will not reduce aldehydes or ketones themselves. And so that makes it very useful. We form an iminium ion in solution, and then we reduce that iminium ion, and that gives us an amine. So we could form primary, secondary, or tertiary amines, depending on what we started with. Ammonia would give a primary amine would give a secondary amine, and a secondary amine would give a tertiary amine. And then we learned that there's two possible combinations of an amine and a carbonyl compound that can be used in reductive amination, and usually either of those possibilities will work. I will say it only works with aldehydes or ketones. You can't do reductive aminations with esters or other carboxylic acid derivatives. Okay? All right, so that covered the way we prepare amines. The next thing we talked about was the relative basicity of amines. Okay? Amines are bases, and we compared the relative basicity. There were lots of comparisons that we performed in class. We compared ammonia to alkylamines. We compared alkylamines to arylamines. We compared alkylamines to amides. We compared different arylamines. We compared pyridine to pyrrole. So you should understand those comparisons. You should be able to rank amines in order of relative basicity. You had a quiz with that. It's probably also something you'll see on the exam. There are some tables in the book on this topic. Table 25.2 and 25.3. So this one here summarizes the 4 factors that we used to make the comparisons. And then this one here, 25.3, was a pKa table showing you the pKa's of the conjugate acids of the amines. So I know I sound like a broken record at this point, but don't memorize the information in these tables. If you understand it, if you can look at those tables and understand why certain amines are more basic than others, and you can explain it to a study partner, then you'll know that you have a very good understanding of this relative basicity concept. Okay? All right, so then we went into reactions of amines, and we started with previously learned reactions of amines. So I won't spend much time on that here, other than just to mention that we can react amines with aldehydes or ketones to generate imines or enamines, depending on the type of amine we have. We can form amides by reacting with acid chlorides or anhydrides. And we learned about, in this chapter, we learned about how you could use those amides as protecting groups. They are useful as protecting groups in Friedel-Crafts reactions. So that was a good example. Then we had the Hofmann elimination. So the Hofmann elimination was a 3-step process where we generated a quaternary ammonium salt with excess iodomethane. We added silver oxide to exchange the iodide for hydroxide. And then we heat that up. Once our counterion to the ammonium salt is a strong base, when we apply heat, we can have an E2 reaction. And if you remember, the key thing with the Hofmann elimination is that it goes against Zaitsev's rule. Zaitsev's rule told us that the more substituted alkene is the major product, and that happens in dehydrations and in dehydrohalogenations, but not in Hofmann eliminations. In Hofmann eliminations, the less substituted alkene is the major product. We explained why that is, and we showed you a figure in class that's not in our textbook, but you should take a look at it on Learning Suite and understand it. In addition to explaining the Hofmann elimination, that figure reminds us about Newman projections and the anti-periplanar geometry and E2 reactions, 2 key topics from the first semester. Okay, so Hofmann elimination allows us to form less substituted alkenes from amines. Okay. Then we had aryl diazonium salts. And we learned reaction conditions for making these. We learned mechanisms. The mechanism was kind of complicated. It had multiple sections to it. So you probably wouldn't have to draw the whole thing from start to finish, but we might ask you to draw the mechanism of one of those sections of formation of an aryl diazonium salt. These are great leaving groups. So you need to know the reaction conditions for making aryl diazonium salts. You need to know the reaction conditions for transforming them, performing those substitution reactions. There was that nice table that wasn't in our book, but is available on Learning Suite that that shows you all the different reaction conditions and the different products that can be formed. And you need to be able to use aryl diazonium salts in synthesis. We showed you numerous examples in class of how aryl diazonium chemistry can be used to access substituted benzenes that you would not be able to access otherwise. In some cases, we can install functional groups like fluorides and iodides that and phenols that we don't have other methods of installing. In other cases, we could install orthopara directors meta to each other by changing the groups and changing the directing properties. So you need to know there's the sequence of reactions, the four-step sequence of reactions we talked about: nitration, nitro group reduction, conversion of the amine to an aryl diazonium, and then substitution of the aryl diazonium. Those 4 steps. And then somewhere in those 4 steps, we will stick another electrophilic aromatic substitution, just depending on the nature of the product we're trying to form. So please make sure you practice that and you're able to use aryl diazonium chemistry in a synthesis. Then another reaction that aryl diazoniums will undergo is the azo coupling. So here you should be able to draw the mechanism, but it's just an electrophilic aromatic substitution mechanism, pretty simple. An important thing to remember here is we need a strongly electron donating or electron rich benzene with either an amine or an alcohol or an ether attached. So, and then we only get the para substituted product. We don't get the ortho substituted product because of the steric hindrance, okay? And then the products of the azo coupling reactions are the azo dyes. And we talked about why they're dyes. They're highly conjugated, so they're colored. And they have to have functional groups that can either hydrogen bond or have electrostatic interactions with the fabrics that they are adhering to. All right, so that's chapter 25. We'll take a break and erase the board, and we will conclude with chapter 26. Okay, chapter 26 is carbon-carbon bond forming reactions. 29, yes. It used to be chapter 26 in the old edition of the textbook, but it is now chapter 29, okay? All right, so this is obviously a very broad topic. Most of the reactions in this chapter involve transition metals. So it allows us to introduce some transition metal chemistry to you. And we started out with the coupling of organocuprates. So we're coupling organocuprates with halides, and we said that we could use pretty much anything other than tertiary alkyl halides. We can use some, but not all, secondary alkyl halides. We can couple alkyl, aryl, or vinyl halides with cuprates. And remember that our organocuprates originate from halides. So this is basically a way of taking 2 halides and coupling them together by converting one of them into an organocuprate. We did not learn the mechanism. The mechanism is complicated. We know it is not SN2. And the most common examples of this, the ones that we showed you, the ones you're likely to see, involve the coupling of an alkyl group with either an aryl or a vinyl group. So we're attaching an alkyl group to a benzene ring or to an alkene. Okay. A key thing about this I should write down, it is stereospecific. So if you have stereochemistry associated with an alkene, either in your cuprate or your halide, that stereochemistry will be retained in the product. Okay. So then we went over an introduction to palladium chemistry. And most of this introduction was not in the textbook. And so hopefully you were taking good notes. You can go back and you can watch the video of today's lecture if you want to get more on that. But most of what we talked about in this section was not in the book, but it is important. It will help you have a better understanding of how these palladium reactions proceed and also why they give the products that they do. So we talked about the 18 electron rule, why palladium, as other transition metals do, wants to have 18 electrons instead of the octet. We talked about the role of ligands, how ligands stabilize palladium, how they help it dissolve in solution, but they are spectators. They're not directly participating in the reactions that are occurring. And then we talked about some processes that occur at palladium. And we paired them up because we have 4 processes and we have 2 pairs of processes that are the reverse of each other. So we have oxidative addition and reductive elimination. So these 2 processes will come together in reactions. And then one important thing to remember about reductive elimination is that proceeds with retention of stereochemistry in the same way that organocuprate couplings do. Your cis or trans stereochemistry of an alkene will be retained in a reductive elimination. And then we talked about alkene insertion. And that's paired up with beta elimination. Okay. So alkene insertion is just an addition step. That's why the opposite of it is an elimination. And this is a syn addition. So there was some stereochemistry here. So this is a syn addition. We also said that palladium bonds to the more substituted carbon. We explained why that is in class. And then our beta elimination usually eliminates a hydrogen, a beta hydrogen, and we have to have a syn coplanar relationship between the beta hydrogen that is eliminating and the palladium because they end up bonded to each other as a result of that. So those were the key details that we talked about in regards to these processes on palladium. So then we started talking about reactions of palladium catalyzed reactions. And the one we talked about today in class is called the Suzuki coupling. And key features of our Suzuki coupling are that we are coupling aryl or vinyl halides and organoboranes. Okay. Usually vinyl or aryl boranes are coupling to each other. So we're ending up making dienes, we're making alkenes conjugated to benzene rings, or we're making biaryl species. Okay. And so a couple of details about the Suzuki coupling. We learned about a process that we didn't mention over here, and that is the transmetallation, the transfer of an aryl or vinyl group from a negatively charged boron to palladium. Okay. And then we also learned that the alkene stereochemistry is retained. It does not change when we perform that reductive elimination reaction. Okay, so there's a few reactions we have yet to cover that we'll cover on Monday. I'll just briefly outline those here. So we have the Heck reaction. Okay, Richard Heck was the chemist who discovered this reaction. He shared the Nobel Prize with Suzuki. It's similar to the Suzuki coupling, but not exactly the same. It involves an aryl or a vinyl halide, just like the Suzuki coupling does. But instead of reacting that with an organoborane, it reacts an aryl or vinyl halide with a terminal alkene or a monosubstituted alkene. Okay? So we're going to generate transalkenes by coupling these species to a terminal alkene. So we're going to add an aryl group or a vinyl group to a monosubstituted alkene. And we'll talk about that. We'll talk about the stereochemistry involved in that. We're going to form transalkenes from this reaction. We'll explain why we form transalkenes. We're also going to learn about the intramolecular Heck. So like the aldol and the claisen, you can perform a Heck reaction in an intramolecular sense. And we'll learn in class that this intramolecular Heck process is useful for forming what we call quaternary carbon centers. These are carbons that bear no hydrogens, that have 4 other carbons attached to them. So they're very hindered, and the intramolecular Heck is a very good way of making those types of compounds. Then we're going to learn about carbenes. So carbenes are reactive intermediates. They have a neutral carbon that only has 6 electrons. So they have 2 groups bonded to them. They have a lone pair, and then they have an empty orbital. So carbenes are very, very reactive, and they can be used to make cyclopropanes. You react carbenes with alkenes, and you generate cyclopropanes. And so we'll talk a little bit about that. We'll talk about a reaction called the Simmons-Smith reaction. The Simmons-Smith reaction uses carbenoids as the reactants. A carbenoid is a species that is not a carbene, but it reacts similar to a carbene. So we'll talk about what that is and how that occurs in class. And then the last reaction we'll talk about is called olefin metathesis. Olefin is an old word for alkene. It's not used as much as alkene is today, but it's still used occasionally. And so olefin metathesis is a reaction. Metathesis means swapping partners. And so there's a couple different types of olefin metatheses. We can react 2 alkenes together to make a new alkene. And then we can have a diene molecule that can undergo a ring closing metathesis process, okay, where we can form, not only can we form 5- and 6-membered rings with ring closing metathesis, but we can actually form macrocycles, very large molecules, via a ring closing metathesis reaction. So olefin metathesis is a very, very useful process. In the Chem 553 class I teach, we spend about a week discussing metathesis chemistry. In this class, we're going to spend about 10 or 15 minutes. So we're only going to scratch the surface of metathesis chemistry. You will learn the mechanism of this, and it will involve curved arrows, unlike the Heck and Suzuki that involve naming the individual steps. The olefin metathesis reaction does have a curved arrow mechanism that we'll show to you. And that will be the conclusion of chapter 29.